Okay, guys. Hi, this is part 3 of Gas 109, and our topic is Maxwell Boltzmann distribution graphs. And your homework is still just the gas test review. And we're going to start with this idea that Maxwell Boltzmann distributions compare average velocities of gas molecules versus number of molecules or particles. And those are at given temperatures. So it's kind of looking at how many gas molecules are going a certain velocity at any given temperature. So there are two kinds that the College Board wants you to know about. So there's two kinds of graphs that you should be able to read and interpret. So the first one is where you have different temperatures. So you have average velocity. Good job, bud.
No, I'm in a sleep.
Oh, here.
Sorry, I'm in a web.
That's okay. There you go. Sorry, I had to help my son. So this is average velocity of the gas molecules in meters per second. And this would be number of molecules. So this obviously is going up, and this is increasing also on the x-axis. Okay, so this first kind of graph would be where you have different temperatures. Okay, and so what is observed is that at a temperature like maybe, let's say this is at 100 or 400 Kelvin, that we have this specific shape of a curve, that it kind of has a peak, that there's an average velocity here, and this might be at 400 Kelvin. So this is at a kind of a lower temperature. And if we increase the temperature, so what we might see is a little bit more spread out. So we could say this would be like 500 Kelvin for our gas. And then as we increase the temperature again, the range of velocities gets bigger, but the number of particles at each velocity decreases. So what we can take away from this is that on average, as temperature goes up, velocity goes up, average velocity goes up, but the range of velocities also increases. As temperature goes up. Okay, so you see a kind of a higher peak for the lower temperatures, and at the higher temperatures, a larger range, so the peak kind of gets flattened out, so to speak. Okay, so that's the first graph, or the first distribution that would be looked at. And the second one is looking at different gases at like temperatures. So this would be different gases at like temperatures. So instead of varying the temperature, what we're doing is changing the gas identification. So this is still number of molecules on the y-axis, and average velocity in meters per second on the x-axis. So that's still looking like that. And what we would see is that the heavier gas molecules are going to have peaks that are a little bit more close together, like this. So this is going to be the heaviest gas, and I'll show this in a different color. And this is at a given temperature. This would be like a medium molar mass gas. And then the lightest gases are going to be have the greatest range of temperature. And hey, good job.
Hey, Mommy.
Just a minute, they're going to have the greatest range of velocities at any given temperature. So if I was going to look at this and maybe identify gases, we could say that this might be xenon, argon, and neon if we were comparing the three of them. But anyway, so this is the lightest gas, this is medium and heaviest. If you were to see a distribution that was even flatter and more widely distributed with the average velocity, then it would be even lighter. So this might be like helium down here. So anyway, you should be able to interpret those types of graphs and be able to look at the different curves and identify who's the heaviest and who's the lightest. And just a couple things you want to take away from this is that the lighter gases, thank you, have greater average velocities. At given temperatures. And they also have a wider range of velocities.
Mommy.
Velocities at any given temperature. Just a minute, bud. Okay, and that is it for Gas 109 Part 3. Thanks.